All right, guys, let's do another divergence theorem example. So here I've got instructions that say I should use the divergence theorem to calculate the flux of a vector field across the surface S. Great. They tell me the field is 3x y squared plus x e to the z plus z cubed. Sorry, throw an ij and a k in there. Those are comments, not pluses. All right, and then S is the surface of the solid bounded by a cylinder. So I think I probably need to draw a picture what this looks like. Let's see. So that is a circular cylinder because to me, this thing here says unit circle. It's in the YZ plane. So I guess what I've got here is a unit circle in the YZ plane. And then they told me it runs from x is -1, so back here. That's x is -1 there, out to x is +2 out here. Okay, so this is the shape I'm talking about, this little cylinder, right? It's toilet paper tube, cool. And it would be annoying to do this without the divergence theorem. I would need to calculate parameterizations for all three of those surfaces, right? Really, there's kind of two end caps, right? So I'd have to do something like S1 is the left end cap, C is the, actually, maybe let's just call it S2. S2 would be the skin of the cylinder, right? So the like toilet paper tube part. And then S3 would be the other end cap. And I'd need normal vectors for all three of those, right? So this one's pretty easy. It sticks straight out of the end. That's going to be something parallel to I. There's another one that's pretty easy. That's this one on the opposite end. That's going to be something parallel to -I. Then the ones around the kind of surface themselves get a little tricksy. I'd need to parameterize the surface, take some partials, get a cross product. The good news is I don't have to do any of that shit because that is a closed surface. And if it's oriented outwards, which it didn't really tell me it is, but I guess I'm going to assume it is, that means I can apply the divergence theorem. So I'm going to say the double integral of this junk, 3xy squared, comma, x e to the z, comma, z cubed, dotted with ds over my surface S is actually equal to the triple integral over the interior of the divergence of that, d volume, and the divergence of that thing is 3y squared plus 0 plus 3z squared, I guess. Oh, well, that's convenient. Let's see. So I guess I can rewrite that as that's equal to 3 times the triple integral. I'm going to need to convert here to, well, hell, man, it's a cylinder, right? So you probably got to convert to cylindrical. Okay, so let's convert to cylindrical. In this case, I'm going to let I'm going to let x be x. I'm going to let y be cosine and z be sine. So that's good, or r cosine and r sine respectively, right? So we're going to convert to cylindrical. I'm going to figure out balance in a second. I'm going to get an r squared out of the y squared plus z squared. And then I'm going to have a times, I think that it's just polar, but with an extra variable, right? So my d volume is an r. That's from the polar part. dr, d theta, d, and my third variable, the one controlling side-to-side movement, is just x. Right, so r makes you go kind of in and out. Theta makes you go around with respect to the zy plane, right? And then x makes you go over. Let's see. So the x's range from -1 to 2. The thetas go all the way around, so 0 to 2 pi there. And the r's range from 0 to 1 because that is a unit circle that I've extruded. Okay, so good news. Some of this is pretty easy. The theta one is just going to toss a 2 pi. So we're just going to womp that guy out of there, and we're going to put a times 2 pi out front. So I'm going to get a 6 pi integrating from -1 to 2. Got an, that is an r cubed, so I'm going to get an r to the 4th over 4. Evaluated from 0 to 1, and a dx. And that's going to give me a 3/2 pi. And then I need the times the integral from -1 to 2 of 1 dx. That's just the length of that interval rather. So that's an interval of length 3. So I'm going to get 9 pi over 2. Check, done. Should be good enough.